Conservation of energy. There are 3 conservation laws in physics: conservation of energy, conservation of momentum, conservation of angular momentum. This is a biggie. When the universe was first created, 13.7 billion years ago, there was a certain amount of energy. That same number is out there today. The total amount of energy has not changed. It's changed form. There's less useful energy than there used to be. Because if you take a match and you burn it, that useful energy that was contained in that match head before you burned it, that's never going to be used. It's never going to be useful again for the remainder of the life of the universe. So as time progresses, there's less and less useful energy, but the total amount of energy stays the same. Well, that's energy conservation at the grand scale. Well, that's very interesting, but it doesn't really help us to solve problems. For us, energy conservation, we're looking at, we want to be able to use it to solve problems. And so we're going to look at it at a smaller scale with some isolated systems. Remember this equation: initial energy plus the net work equals the final energy. When we say energy is conserved when the net work is 0. So when there's no net outside work done on a system, the total energy remains constant. It may change form from kinetic energy to potential energy and then back again. But the total energy remains the same. If I do this uber exciting physics demo right here, right, when the whiteboard marker leaves my hand, it has kinetic energy. As it goes up, it loses its speed, so it loses kinetic energy, but it gains height, so it gains potential energy. Until it gets to the very top, it no longer has any kinetic energy, but it has the energy of height, which is potential energy. And then it comes back down. And it loses that potential energy, but it's transformed into kinetic energy until it gets back down to my hand where it no longer has any potential energy, it just has kinetic. And then I catch it. So as the whiteboard marker is traveling through the air, there's no force acting on it other than gravity. And so energy is conserved. There's no net work being done on it. Now, while I'm throwing it in the air, my hand applies a force. So energy is not conserved in that situation. But after it leaves my hand, while it's in the air, energy is conserved. So if energy is conserved, then you can say that the initial energy equals the final energy, and it equals some constant. That's the idea behind energy conservation. If you have somebody on a 10-meter high platform, and they're going to dive into the water 10 meters below. So here's Jeremy. He's going to go down into the water. He starts at rest, so his initial velocity is 0. Let's say that Jeremy has a mass of 100 kilograms.
Please report to the attendance office. Jezreel Fournette, please go to the attendance office.
So let's say that we have Jeremy here. He's stepping off of a 10-meter high platform. So this is his initial position is 10 meters above the water. He starts from rest, and he's going to plummet into the water here. He has a mass of 100 kilograms. What happens to his energy? Well, his initial energy is going to be, well, remember that total energy is KEI plus UGI. But he doesn't have any speed at first, and so that's, the energy of speed is kinetic, so that's 0. So all he has is mass times, this is UGI, mass times G times Y. I'm going off to the side because I need the space down here. So his mass is 100 kilograms times G. I'm going to use a G of 10 instead of 9.8 to make the math easier. 10 meters per second squared times the height of 10 meters And when I multiply 100 times 10, that's 1,000 times another 10 is 10,000 joules. So he has 10,000 joules of energy. And it's all potential energy at first, right? So this is, that number is 10,000. That number is 0. And they add up to 10,000 joules. Well, what's it look like when he gets down here, which is just 3/4 of the way? And then what's it look like when he's halfway down? And then what's look like when he's at quarter of his height? So this is what? 2.5 meters, 5 meters, 7.5 meters. And then just before he hits the water, what's that energy look like? Well, when he's down here, energy is conserved as he goes through the air. What's his potential energy at 7.5 meters? Well, it's going to be M. I'll calculate it to the side, and then I won't need to do this again after this. So when he's down here at 7.5 meters, you've got 100 times 10 times 7.5. Whoopsies. What's 100 times 10? That's 1,000 times 7.5. That is 7,500 joules. But wait a second, energy is conserved. His total energy is 10,000 joules. So at this point, he's got a total energy of 10,000 joules. But he only has 7,500 joules of potential energy. Where did the other 2,500 joules go to? They went into kinetic energy. He's speeding up as he falls. And so this is 2,500 joules of kinetic energy and his remaining 7,500 joules of potential energy. When he's halfway down, at that point right here, he still has 10,000 joules of energy total. But he's halfway down, so now that's 100 times 10 times 5, which is 5,000 joules of potential energy. Where did the rest of the energy go to? It went into the energy of his speed, his kinetic energy. So now he's gaining kinetic energy and losing potential energy, right? This is potential, that's kinetic. At the 2.5 meter mark, he still has 10,000 joules. Hopefully you see the trend here. 10,000 joules of total energy. Well, what's going on? Now he's got 7,500 joules of kinetic energy and 2,500 joules of potential energy. How do I know that? Because 2.5 times mass times g is 2,500. The rest of it's potential, or kinetic, sorry. Notice they always add up to the same number. Energy is conserved. And then just before striking the water, this is still 10,000.
Jezreel Fornes, please come to the attendance office. Jezreel Fornes, please come to the attendance office.
Just before striking the water. Just before striking the water, he still has 10,000 joules of energy. He has no height. And so all of the energy is kinetic. That's when he's traveling the fastest. So this is 0. This is 10,000 joules. So the point of this exercise is that he's gone. This is kind of ugly up here, and I apologize for that. Let's erase this. He's gone from initial energy of 10,000 joules. None of it was kinetic. It was all potential. And then as he falls, he's losing height, and so he's losing potential. So this is his potential energy, and that's his kinetic energy, and that's his total energy. Total energy is kinetic plus potential. The total never changes. He gains speed, so he gains kinetic energy as he loses the potential energy. Energy is conserved during the entire trip. Once he goes splat in the water does work on him. Energy is not conserved in that situation.